how should we define differentiability for a multivariable function? In this video, we're going to look back at single variable calculus and try to figure out what problems differentiability was trying to solve, and try to solve those same problems in the higher dimensional analog. And I'll note that in the previous video, we saw that even if partial derivatives existed, this wasn't perhaps enough to get to a full notion of differentiability. And so we really need to do something more. That's what the point of this video is. So let's begin our journey into differentiability of multivariable functions by looking at single variable functions first to build up some intuition. So let's just remind ourselves about the definition of the derivative. A few different components. We're going to say the derivative of a function at some point x naught was the limit as h goes to 0, what I call the difference quotient. The numerator has this difference, f of x naught plus h minus f of x naught, and the denominator has the value of h. Now, this formula is all fine, but what I really want to illustrate is the picture that goes behind it, and I'll remind you that as well. So imagine you have some function, this is 1 minus x squared, and then imagine that you put those 2 points on, the points above x naught and x naught plus h, directly on the graph. And what you can get is a secant line. You have the point x naught, f of x naught, and x naught plus h, f of x naught plus h. You have those 2 points labeled. You draw the secant line that goes between them. And then what's the value of the h? Well, the h represents this width on the x-axis that represents the change in the run, if you will. So the slope of that secant line is rise over run. That is, what the difference quotient represents is it represents the slope of the secant line. And then the limit says, well, what happens if the x naught plus h and the x naught get closer and closer and closer and closer and closer together? Then we will define the tangent line, which is going to be the limit of the slopes of these secant lines. That was how we defined differentiability in the past. And if this limit existed, then our function was defined to be differentiable. And it meant it was relatively nice. You didn't have any sort of weird sort of cusps or jumps or spikes or anything bizarre happening at this point x naught, because you could sort of put this nice tangent line on that just come along and kiss the curve. The curve had to be relatively nice for this to be able to occur. So that was one view of differentiability, probably the most common way that it was presented. But I want to take a different view of differentiability of a single variable function. I'm going to take this limit expression, and I'm going to just sort of rearrange it a little bit. It really looks almost the exact same thing, but a few little details have changed. So first thing I did was I took the h on the bottom and I multiplied it up, so I had an f prime of x naught times an h. And then in place of a limit, what I did instead was write e of h, which stands for an error term. And I'm going to have the condition that that error term, that e of h, is small, in the sense that even when you divide out by that h, the limit always has a division by h on the bottom, even when you divide out by that h, that this error term is so small that it's going to 0 as h goes to 0. And okay, so really what is this error term? Basically the idea is when you think about the difference, the f of x naught plus h minus the f of x naught, that is an actual difference on the actual function, an actual difference in heights. And you are approximating that difference in heights by the f prime of x naught times h, and the error is just the error between those. So on the actual graph, what it looks like is the difference between the value on the actual function and going up to that tangent line. When you approximate it by the tangent line, how much of an error are you making? So mathematically, these two statements are just the same thing. It's just different ways of trying to write down the limiting process. One writes it explicitly at the front and the other has an error term that goes away. Other than that, they're the same. So they have a nice sort of little philosophical shift in perspective. In this new way of thinking about it with errors, I can say that I really have this difference approximated by some approximation. That's what the f prime times h is. It's an approximation for the amount of change. And then that approximation for the amount of change is not completely accurate. It's got some error term. And that error term e of h is what we have here. And the error term is, if it's differentiable, something so small that even when you divide it by h, which is going to 0, that the limit is still going to be equal to 0. So a very small error term, at least when h is very small. Okay. Now the reason why I'm going back to this single variable calculus case is we want to get to multivariable differentiation. And I'm actually going to use the second of these two perspectives to come up with my definition of the differentiation of a multivariable function. So let's jump now to a multivariable function. It's almost exactly the same. Except instead of 1 minus x squared, I have the 1 minus x squared minus y squared, so I get this nice surface. And then what I'm doing here is I'm considering some point, not just x naught, but x naught comma y naught, a point in 2 dimensions. And the formula I've put up here is the partial derivative of f with respect to x at the point x naught, y naught. And indeed, again, it's defined in the same sort of way that we've seen in the past. It's just the limit as h goes to 0, where in the y component, you say it's a partial derivative with respect to x. We're keeping y fixed. Y doesn't change, just y naught. But in the x component, it goes from x naught to x naught plus h in your difference quotient. And then visually, we get basically the same picture we just had. The pink lines represent the secant lines, and the slopes of the secant lines approach the slope of the red line, which is the tangent, as h is going to 0. So partial derivatives and derivatives of single variable functions are really very similar. And the reason for this is that a partial derivative just says, let's just fix the y value, imagine just a fixed number, and then the function just becomes a single variable function, it's only x that's changing, and so the pictures really align very nicely. I did this for the partial derivative with respect to x, but we have a partial derivative with respect to x and y. At your point x naught, y naught, you can slice with respect to x, and you can slice with respect to y. You get sort of 2 different curves, they each have 2 different tangents. Those are the partial derivatives with respect to x and y, respectively. Okay, so let's go back to just focusing on the one with x. I now want to do just a very slight shift in notation. I'm going to be imagining changing x and y in a moment. So instead of having h as the symbol for my little change, I'm going to take all the h's and I'm going to replace them with delta x's instead. The argument here is that I'm going to have a delta y in a moment. Okay, so let's get up some space here. So I've got my expression. And now what I want to do is I want to rewrite this in terms of errors, just as I did previously. So, okay, doing that looks like the following. The difference is now the thing you approximate, that's that partial derivative times the delta x, plus an error term. We'll call it E1, because we're going to have 2 error terms in a moment. The error term that is a function of delta x. And indeed, I really do want to think of this rewriting of that formula as having this approximation term. That's what the partial derivative represents. It's approximating the change that you're going to make when you shift over by delta x. And then that approximation term is still an approximation because it's also got this error term. And we've seen that the error term needs to be small in an appropriate sense. Okay, so that's the partial derivative with respect to x. Let me put it just there by itself. But we could also write down the partial derivative with respect to y. It's going to be the exact same story. It's just that the y naught is changing to y naught plus delta y. And as a result, that you're going to get this approximation in terms of the partial derivative with respect to y, and then an error term in terms of delta y. Now here's the big moment. Here's the moment we actually get to differentiability. So I want to consider a difference where I am now changing the x naught, y naught to x naught plus delta x and y naught plus delta y. As in, what's changing here is I'm imagining both the delta x and the delta y change. That I'm taking my one point and moving it in 2 different directions at the same time. The sort of problem of partial derivatives was they sort of were too restrictive. They only look when you're changing x by itself or y by itself. And now we really want to think of both of these things changing at the same time. So the argument here is that when you change x, well, we have this approximation in terms of the partial derivative with respect to x that you get. When you change y, well, we have the approximation of the effect that that has in terms of changing y. So what if I set this to be the sum of those 2 things? That is, I have a component which is the change in x and the component which is the change in y, and the error from changing x and the error from changing y. And indeed, if I add just a couple more things, let me give myself a bit more space. I will now formally define that f is differentiable at some point if this long expression that I have is true and that the errors are appropriately small. In other words, I need to say that the limit of the E1 divided by the delta x is 0 and that the limit of the E2 divided by the delta y is equal to 0. I need to have both of those things being true. So that is my definition of differentiability. And actually, let's just walk through it one more time just to make sure we're all confident. The first thing we want to focus on is this difference. That's what I've been studying all along. I want to know what is the difference between the function when you change from one point to another. In this case, x naught, y naught to x naught plus delta x and y naught plus delta y. And then what we're saying is that this difference can be approximated by these two expressions with the partials. There's the change with respect to x, the partial derivative with respect to x times the delta x. That's sort of the approximation of the contributions from changing x. And then we approximate the contribution from changing y by the partial derivative with respect to y times delta y. These are approximations, so they have two error terms. There's an error term from the approximation in terms of x and in terms of y. But these error terms are small in the sense that these limits of these error terms are both going to zero. And in fact, they go to zero fast. Even when you divide out by delta x or delta y, which are themselves going to zero, even then, they're still going to zero. So these error terms have to be really small, at least as delta x and delta y are going to zero. If you have that, then you have differentiability. All right, let's see an example. I actually want to return to this example that we saw in the previous video of the cross. And I'll remind you that this example is a discontinuous function, but that the partial derivatives both exist, because when you look down the one axis or look down the other axis, the function just looks like one there. It's defined to be one along the axis. And so according to the partial derivatives, and that's the computation I put up here, the partial derivatives think this is just a horizontal slope of zero. And that was a problem for us because it sort of violated our intuition that discontinuous function should not be differentiable. But here this discontinuous function had existing partial derivatives. But here's the issue. If I focus in on what's happening on the shift when I only change in terms of h, this f of 0 plus h and 0, well, what's happening there is it's quite a special case because I did not change the y at all. If I imagine changing x and y, like we did in the definition of differentiability, then it would shift off the axes now because both components were changing. So the special case of partial derivatives is about to go away. Okay, indeed, let's go and try to do this by writing out that definition of differentiability, and we'll see whether or not the error terms are indeed small. So I put this all in. The point is 0, 0. The shift is delta x and delta y, and I've got this expression for the partial derivatives. As we've computed, both partial derivatives are 0. So I can simplify this a lot by getting rid of those partial derivatives, and it's just a 0 plus a 0. In the difference, well, f of 0, 0 is 1. And f of delta x delta y, this is generically some point which is not on the axes. So generally it's going to be, well, 0 because it's not on the axes. So what I have on the left is 0 minus 1, minus 1. On the right, I just have some two error terms. Now, here's the point. Those error terms, if it's differentiable, have to be small. And the limit as delta x and delta y are going to 0. But they cannot be small because they have to add up to minus 1. Minus 1 is not close to 0. So the point here is that these error terms cannot both be small. And as a result of this, it's not differentiable. The attempt to write down that formula for differentiability did not give small errors, and so it was not differentiable. So now we've resolved the tension in our story. Well, the example previously had a discontinuous function with existing partials. We now see that it's because partials are too limiting. They don't see the problems. But differentiability, the full differentiability, does see the problem here. And so this discontinuous function is not differentiable as we would have expected from Calculus 1. So I might have left you with the sense that partial derivatives are a bit useless, but in fact they still are. And they still are because of this very powerful theorem. It says that if the partial derivatives are continuous, they at least have to exist, but if they exist and in addition are continuous on some open region R, then the function is differentiable on that region R as well. And the reason why this theorem is so powerful is that partial derivatives are generally quite computable. So you can go and compute the partial derivatives, and if those partial derivatives don't have problems, that is, if the partial derivatives are continuous, then you get differentiability for free. So most of the time you want to prove a function is differentiable, you just compute the partial derivatives, say they're continuous, and boom, you have it. And then it has to be sort of pathological examples like this cross one that I've talked about, where you can have these fringe cases where the partial derivatives exist despite the function not being differentiable.